All right, thanks for the, oh, there we go. Continue. Okay, thanks for the introduction, Emily, and thanks for giving me the opportunity to speak here today. As Emily said, I'll be talking about some work on triangulating exotic four manifolds. So I'll just give a bit of a brief overview of why four manifold topology is a bit of a wild place to work in. And then I'll sort of speak a little bit about what I've done and some current ongoing work. So a basic problem in topology, right, is the classification of manifolds. And this depends very much so on, the dimension that you work in and the type of manifold you're looking at. So for example, in dimensions less than or equal to 3, the behavior of manifolds is largely captured geometrically. So for example, compact orientable surfaces can be classified by their genus. And then in dimensions greater than or equal to 5, algebra and surgery theoretic methods tend to dominate. So the behavior of manifolds is dictated by algebra in these settings. But the situation is quite different in 4 dimensions. So for example, any finitely representable group can appear as the fundamental group of a 4 manifold. And determining whether 2 finitely represented groups are isomorphic is provably an undecidable problem. This is due to a result of Adian and Rabin in the 50s. As a consequence of this, it means that there's no algorithm that can ever tell you whether 2 arbitrary closed 4 manifolds are diffeomorphic. So there's just no conceivable list that you can write down of 4 manifolds in the same way that you might for surfaces or 3 manifolds or high dimensional manifolds. Now, this being said, simply connected topological 4 manifolds were classified by Friedman in the 1980s. However, dimension 4 is the first dimension where we actually have a distinction between the smooth and topological categories. So smooth 4 manifolds are still a bit of a mystery to us. So I'll be talking mostly about exotic manifolds. So for us, exotic manifolds are manifolds which are homeomorphic but not diffeomorphic. So topologically, they're the same thing, but there's no smooth deformation of one into the other. So the one example of this is of also why dimension 4 is a strange place to be in, is that even just bog ordinary Euclidean space, nothing particularly interesting about it, just ordinary old Euclidean space, in any other dimension other than 4, Euclidean space admits a unique smooth structure. But in dimension 4, Euclidean space admits uncountably many smooth structures. So not just multiple, not just a few, not just countably many, but uncountably many, which I find like completely crazy. So sort of the picture to have in your head, right, is that if, I don't know, Alice and Bob here are in their respective manifolds, when you have your topological hat on, you see the same thing from each manifold. So continuous functions on one manifold look like continuous functions on another. There's a one-to-one correspondence, right? But if we put our smooth hats on, then they look like completely different beasts. So now the space of smooth functions, like they're completely different entities. Okay, so if this doesn't keep you awake at night, I don't know what will. So here's some like big picture motivation for all this. So the big picture motivation is the generalized Poincare conjecture. So I'm sure we've all heard of the Poincare conjecture in one form or another. So the generalized form is fix your favorite category of manifold, then the statement, so whether it's topological or piecewise linear or smooth. And so then the statement is that every closed n manifold homotopy equivalent to the n sphere in your favorite category is isomorphic in that category to the standard n sphere. And this really, really, really does depend on the category you work in and the dimension you work in. So for example, if we work in space of topological manifolds, this is known to be true in all dimensions. If you work in the setting of piecewise linear manifolds, then it's true in dimensions other than 4, where it's currently an open problem. In the smooth setting, it's false in general. It's true in most low dimensions. The first known counterexample is in dimension 7 with Milnor's exotic spheres that you might have heard of. And it's unknown in dimension 4, where again, it's an open problem and where smooth and piecewise linear coincide. So finding an exotic 4 sphere would be a counterexample to this generalized smooth Poincare conjecture, and would be the sort of final brick or final nail in this particular problem. So is there any hope, right? Is there any hope? There is some degree of hope, at least for if you like working with computers, maybe, in the sense that we know that every smooth manifold is uniquely triangulizable, so admits a PL structure. And by various results from leading up into the 60s, we know that for dimensions less than or equal to 6, PL manifolds can be uniquely smooth, so admit a smooth structure. So in particular, PL and smooth are equivalent for 4 manifolds, which means the hope that we have is that we can maybe gain an understanding of 4 manifolds or smooth 4 manifolds or exotic 4 manifolds via combinatorial and computational methods. That's sort of the big hope or idea behind all of this. Okay, so I want to talk about a specific class of 4 manifolds now. Now, I'm sure everyone here knows what a knot and a link is, but just so that we're all on the same page, a knot for us is a copy of the circle embedded in the 3 sphere, considered up to smooth isotopy. So, and then a link is just going to be a disjoint union of possibly interlinking knots. So here an example of what we think of for knots and links. Okay, now what we then want to consider is a framing on these objects. So a framing on a knot is a choice of trivialization of the normal disk bundle. What this basically amounts to in practice is if you imagine your knot, and then if you imagine a parallel copy of your knot pushed off from that, then a framing is basically, so this then generates, this is basically like your like a normal vector field. You can think of that generating a normal vector field to your knot. And then a framing we can parameterize by the number of times this push off or this vector field twists around the knot. Okay, so here's a picture of what we're doing here. So we might not always draw like the parallel push off twisting around. Sometimes we'll indicate by a box with an integer in it the number of twists, or sometimes we might even just put an integer next to the knot diagram to denote the framing. Okay. So here's a particular class of 4 manifolds associated to framed links. So given a framed link, we can build a 4 manifold from this, sometimes called the link trace or the knot trace, depending on who you talk to. And it's built as follows. So take a copy of the 4 ball, so just D4, and we glue on copies of D2 cross D2 via this embedding. So basically what we do is this map sends us from the boundary of one of the components of D2 cross D2 into the boundary of D4. So the boundary of D2 is just S1, the boundary of D4 is just S3. And so this map satisfies that on basically the core or of this D2 of this disk. So on S1 cross 0, we get back our link component, and in a neighborhood of that, then phi has we have basically linking number in a neighborhood equal to CI, so equal to the framing. Okay, so the idea, if this is a bit hard to visualize, the idea is that we've got D4, we stick on this, well, basically another topologically it's just another copy of D4. On the core, we've got a knot or a link, and in a neighborhood of that knot or link component, it's twisting around according to the framing of our framed link. Okay, so the point though is that these are 4 manifolds we can visualize as link diagrams decorated with integers on each component, so as a framed link. And via this construction, there's that one-to-one correspondence between the 2 objects. So here are some examples now. I just want to give some examples of well, of both 2 handle bodies of these link traces, but also of exotic pairs. Okay, so this first pair is an exotic homotopy punctured CP2 bar, so complex projective plane type thing. And this is the first known sort of exotic pair of this form, Rhuaidi Burke in the early 90s. I should also mention it's the smallest known exotic pair, where smallest in this context means, well, smallest with respect to Euler characteristic or second Betti number, or even just in terms of the link diagrams, really. These are pretty much the smallest known examples that we have. Now, I'm not going to go into why these objects are exotic. Maybe I can sort of talk about that a little bit with one example, but maybe just take my word for it that these are in fact homeomorphic, but not diffeomorphic. Here's another example, due to Yasui in 2015. This is like a sort of like a disk bundle over the sphere. And again, you can also see this, the link diagrams of these things get quite complicated in terms of the number of crossings and, you know, the number of twists and things that are going on here. Here's another example. This is the smallest nuclei of the elliptic surface E3 in particular. So the exotic nuclei. This is due to Gompf again in the early 90s. Now, because I know I've got I can maybe go a little bit over time today. I can maybe explain just super briefly as to convince you as to why maybe this pair at least might be exotic. We can determine that they're homeomorphic basically by, in this case, for two handle bodies, the topological properties are basically encoded via the linking matrices of the link diagrams. And for two handle bodies, this just amounts to basically the either the intersection number of the links and the framings on each component. Now, without writing it all down, it's not hard to maybe convince yourself that if you write down the intersection matrices of these two components, of these two links, it's not too difficult to show that they're isomorphic. And by a result due to Friedman, if simply connected topological form manifolds have isomorphic intersection matrices, then they're in fact homeomorphic. Why they're not diffeomorphic amounts to, in the world of form manifolds, and in particular expressed in the as framed link diagrams, there are a number of moves that we have. So there's this notion of Kirby calculus, which people may or may not have heard of. Basically, it's sort of, you can think of them as basically Reidemeister type moves, but for the associated form manifolds. I mean, it's maybe that's maybe simplifying things a bit too much, but there's a number of moves which basically amounts to, if you can get from one diagram to the other by this allowable set of moves, then they represent diffeomorphic form manifolds. So these are things like adding handles, canceling handles, if you know about handle decompositions. But one move in particular is adding a copy of an unknot with plus or minus one framing. And this amounts to blowing up by CP2, so by adding summing with the complex projective plane. And so if you look at these two diagrams here on this slide, you can see that the one on the right has this unknot component linked with the other component with minus one framing. So this is sort of like a copy of like a CP2 connect summoned. And so one of the allowable moves in Kirby calculus and form manifolds is that I can slide this guy off, and that represents like a direct sum. So this thing on the right admits some kind of prime or connect sum decomposition. Whereas if you look at the diagram on the left, you see that the framing is different on that unknot component, so it doesn't represent like a CP2 summoned. There's no way I can manipulate this diagram to peel off a copy of CP2. So the thing on the left doesn't decompose any further in the same way that the guy on the right decomposes into CP2 connect sum with something else. So they can't be diffeomorphic form manifolds. So that's the sort of that's probably the easiest argument that you'll ever see as to why maybe two form manifolds aren't diffeomorphic. A lot of the time, to prove something is or isn't diffeomorphic, you need to resort to very, very heavy machinery, like gauge theoretic machinery, counting solutions to nonlinear PDEs. It's very, it becomes very, very unwieldy very quickly. So this is probably the simplest proof you'll ever see of something like that. So hopefully, though, that this maybe convinces you that these are in fact homeomorphic but not diffeomorphic, more or less. Okay, and finally, here's just another example of some connect sums of punctured CP2s and other bits and bobs. And this is due to Noe in 2017. And so the point of all this, though, is just to show you some examples that of exotic four manifold pairs, I guess. And so, and the other point, though, is that I've just shown you a bunch of diagrams and said, okay, here are some examples of smooth exotic four manifolds. But I said right at the start, right, what we want to do is maybe try and study these things combinatorially via computational methods. So that means, right, that you need combinatorial representations of these objects. But up until now, we basically we don't have any such representations or representatives of these objects. So there was, up until now, one readily available example due to Kornheimer and Rofka, again in the sort of mid-90s. This is the exotic pair here. So it's the real projective space connects some with the K3 surface, which is sort of like another prime fundamental four manifold. And then the other pair, part of the pair is RP4, connect some with 11 copies of S2 cross S2. And so it's easy enough to triangulate RP4 and the K3 surface and S2 cross S2. These are all quite basic objects, basic four manifolds, and it's trivial enough to then form the connect sums of these objects. So it's fairly straightforward to produce this pair. But the main problem is that after this, there's really no systematic way of generating triangulations of smooth four manifolds or two handle bodies from framed link diagrams, let alone exotic four manifolds. And so now let me tell you about a method for triangulating four manifolds. And in fact, a method for triangulating any dimension manifold that you like, really. And so this is called crystallization theory, and it allows us to represent PL manifolds by edge-colored graphs. For me, in this setting, an edge-colored graph is a finite multigraph. So I allow multiple edges coming out of the same nodes, but no loops, and a surjective map from the edges into basically a set of colors where no two adjacent edges have the same color. So here's an example here of what I'm sort of thinking of when I say a colored graph. And so now let me tell you how you get a triangulation of a manifold from an edge colored graph. So for each node in your colored graph, you take a corresponding n-dimensional simplex and you label its vertices by the color set. So here's an example of the three-dimensional case. Okay, because we can all picture three dimensions, that's easy enough to do. So if I have a vertex V, I then generate a tetrahedron and I label its vertices just by my color set 0, 1, 2, 3. And so then if I have two vertices or two nodes in my edge colored graph, if they're joined by a C colored edge, I identify the n-1 dimensional facets of my two corresponding simplices opposite to that C labeled vertex, so that equally labeled vertices coincide. So again, here's an example in 3 dimensions. So I just identify the two triangles opposite to the C labeled vertex there. Okay, and in this way, I can build a manifold from my colored graph. Really, what's going on here? Basically, what this colored graph is, you might, if you're wondering, is it's effectively like the one skeleton of the dual graph of the manifold. That's sort of what this thing is. And so here's basically the magic underlying what I've managed to do. So Casali and Cristofori in 2000 and more recently this year in another paper described an algorithm for producing colored graphs representing two handle bodies straight from their link diagrams. So without going into all the nitty-gritty details of the algorithm itself, Here's sort of like the crux of it on the screen here of what you do. So for each crossing in the diagram, you build sort of this order 8 graph as follows. And in order to encode the framing on the link diagram, what you do is you add trivial Reidemeister 1, so trivial twists to your link diagram, so that then the right of the diagram equals the framing. That's how you encode the framing. So if you've got these twists, you build a different type of graph. You do some substitutions later on to sort of finish things off in the 4-dimensional setting. But anyway, the thing is that there was no readily available actual implementation of this algorithm. It was proven to work theoretically, but there was no actual, you couldn't actually just go off and use this thing. So what I've done is I've now actually implemented this algorithm in a software package in C++. It'll be part of the, I think, Regina software package, if you're familiar with Regina, later on in a future release, and also hopefully a standalone release soon-ish. So we have support for both 3 manifolds and 4 manifolds. So for 3 manifolds, you can also get 3 manifolds from framed links, and the result there is what you get from integer Dane surgery on the link. You can build various types of 2-handle bodies with or without boundary, different types of boundary, so real or ideal. It'll build you either the colored graph itself, so it'll produce an edge list to build the colored graph, or it'll produce a Regina compatible triangulation. And so this now gives us a systematic way of quickly generating triangulations of 2-handle bodies, or 3 manifolds, if you like. And in particular, this has now allowed me to generate triangulations of the exotic 4 manifold pairs I've shown you before. In a different version of this talk, I then go off and give a live software demonstration, but to save on time and just for, you know, not to bore everyone, I guess, you know, here's sort of what the interface looks like if you're curious. What I want to talk a bit more about just in the last little bit of time, though, is some of my ongoing research and sort of directions for future research. So obviously, one thing we want to do is build more exotic pairs to sort of study these things combinatorially. The other thing that we want to do is the resulting triangulations that you get from this algorithm via the colored graph routine. The resulting manifolds and the resulting triangulations are by no means minimal. So it means that it becomes very difficult to analyze these things. So one thing that we want to do is construct smaller triangulations of these things, ideally minimal with respect to some metric. We'd like to broaden this to a wider class of 4 manifolds. So if you're familiar with handle body decompositions, basically everything I've been talking about here is just gluing 2 handles onto the 4 ball. We'd like to also then, if we can introduce 1 handles, that'll allow us to capture a much wider class of 4 manifolds. In fact, we hit nearly everything if we can implement 1 handle support. I'll talk a bit more about this in a second. Ideally, also, we want to investigate quarks and related objects. These are currently what's understood to give rise to exoticness. So again, I'll talk about this in a moment. So we would like to be able to investigate these things combinatorially, and really blue sky thinking is if we could investigate some kind of feasible PL invariant to distinguish these things. At the moment, there are some maybe like graph theoretic invariants that we can investigate, but that's sort of way down the track. Because as I said earlier on, the smooth invariants used to distinguish 4 manifolds are by and large not particularly practical or computably useful. Because like I said, it involves things like counting solutions to nonlinear PDEs and that sort of thing. Okay, so let me just talk a little bit about where we're going with this in terms of what we've managed to do so far. Okay, so the triangulations that I've been that come out of this edge colored graph routine are basically like simplicial complexes, and so you need a lot of simplices in order to sort of build things as a simplicial complex. So, but if we widen our definition of a triangulation to this notion of a generalized triangulation, where now basically I'm allowed to glue faces of the same simplex to itself. Basically I'm allowed a bit more freedom in how I can glue things together. So this then allows me to build far more economic sized triangulations. So if you allow for generalized triangulations, which is also what Regina uses, by the way, if you use triangulations in Regina. So if you've got a four manifold, a generalized triangulation of a four manifold, let Fi be the number of I-dimensional simplices in the triangulation. If you have a one vertex, one edge triangulation, then the F vector is completely determined by the second Betti number of the triangulation. So here it is here, and this is not too difficult to prove. It's largely an exercise in pushing around Dane-Somerville relations and solving a linear system. It's pretty straightforward. Now, such a triangulation is obviously minimal with respect to vertices and edges. You need at least one of these things, right? You need at least one vertex, one edge. So you can't get any better than one. Now, they're not necessarily minimal with respect to pentachora, but if the sort of idea that I have here is that if you can get down to one vertex and one edge, at least it fixes the everything, the F vector completely, so you know precisely what you can get down to. And so at least it gives you a bit of a benchmark to sort of work with. So using a custom heuristic, which performs sequences, a certain sequence of Pachner moves or bistellar flips, I've actually been able to get down to one vertex, one edge triangulations of three of the exotic pairs I showed you before. So the bullet pair, the exotic nuclei, and that other CP2 connect some looking thing. So and you can see compared to the original F vectors, which the algorithm produces, this is still pretty good going, even with respect to the number of pentachora. So when you're looking at things like 132 or 148 pentachora, 14, 20, 26, pretty good going. But still more work to be done here. One handles, like I said, very, very, very recent work. So past couple of weeks recent, and actually I don't think it's even out on the archive yet, of Casali and Cristofori have extended this algorithm to four manifolds with one handles. So I've started work of implementing this in software. So hopefully when I've got this up and running, I'll have even more interesting stuff to talk about. But in the meantime, here's just to finish off a little teaser of why this is a big deal, which is quarks. Okay, so I said before, quarks are basically what we understand to basically be the sort of the core bit of the four manifold, which gives rise to exoticness. So it's a compact contractible manifold with an involution on its boundary, such that it extends to it extends to a self-homeomorphism of the quark, but not to a self-diffeomorphism. So this is sort of, you can see sort of maybe where this is, how this works then. So if you've got a quark, you've got a quark in four manifold, if when you cut out the quark and reglue it via this involution, it produces an exotic copy. So then this sort of extends to a homeomorphism then of the whole manifold, but not a diffeomorphism. So here's a picture of a quark. I won't explain why or prove it or anything, but just take my word for it. Here's so you can see though, so the quark itself is this zero framed two handle, and then this dotted unknot is the one handle. And then this gamma loop is sort of, if you've got a loop on one of the components, then the involution on this on the manifold basically exchanges the gamma loop exchanges the where it sits on one of these components. So you can actually write this, the quark, you can actually draw it as a symmetric link, and then the involution is basically a 180 degree like a rotation about sort of the symmetric axis, and then and then like a rotation or something. It's fairly simple to describe, but basically what it amounts to then is an interchanging the components of where the loop sits. In particular, the ACT bullet pair that I showed you earlier on, so A1 and A2, this actually comes from a cork as follows. So if you stick a -1 framed 2 handle on the cork here, then via a bit of Kirby calculus, a bit of handle cancellation, you can get down to A1. You hit this thing with this involution, which sends that -1 framed 2 handle to the other component. Again, you do a bit of handle calculus, well, a bit more involved handle calculus. It gives you that other manifold A2 that I showed you. So using this extended algorithm, I've actually already triangulated the cork, or this cork, as well as A1 and A2 in their cork form. Still investigating, you know, what's going on here. But one thing that I'll just quickly mention is here's a picture of A1 with 14 pentachora and A2 with 14 pentachora. I've managed to simplify the cork down to 10 pentachora. Now you can see, hopefully, if I zoom in here, now I should mention, this is all conjecture at this point, more or less, but you can at least see from these triangulations. So these are the dual graphs of the manifolds. In these 14 pentachora triangulations, A1 and A2, you can see something on each of these, which looks suspiciously like this 10 pentachora triangulation of the cork. So it looks like, again, this is all just conjecture, but it looks like, well, I don't know, it looks like the cork really is sort of sitting there in broad daylight, right? And so, I mean, we're doing things like trying to pin down what the combinatorial interpretation of the involution is and sort of other things. But this is sort of a bit exciting. This is a bit exciting, the fact that it's sitting there sort of in broad daylight, or at least we sort of suspect that that's what's going on here. And for example, right, because these guys are sort of built from, like I said earlier, the unknot with ±1 framing on it is like plus or minus CP2. I kind of conjecture, right, that if we cut things in the right way, you'll actually be able to just get like the cork sitting on its own and a 4 pentachoron, which would be a minimal triangulation of CP2 sort of just sitting in. And if we could figure out what the involution was, or the right way to glue these things together, then that would give us sort of like a really sort of strong combinatorial interpretation as to sort of the structure of these manifolds. And okay, just to finish off lastly, here's another picture of A2 in it's got 20 pentachora. I have absolutely nothing intelligent to say about this thing. I just thought it looked really interesting because, again, you've got this thing that looks like the cork sitting up the top here, and this interesting sort of structure. I don't know. I don't even know what's going on here, right? I just thought this was a really interesting picture, and that's what I'll finish on. So who knows where this is all headed. So yeah, thanks for listening. That's all I got.
Thank you, Rhuaidi. That was great. Does anyone have any questions?
Yeah.
No, you go, Yossi.
You go.
Oh, no, you go.
Nah, you go.
Okay, I'll go. My question is really dumb. I just want to clarify my understanding of something. So, you implemented this in C++, but I always figured that Python was the better thing to do. So
the very first version of this was in Python and Sage, and then specifically it was in Python 2,
right,
and Sage, and then Sage updated, so it would only use Python 3. So then I had to update everything to Python 3. How hard could that be? As it turns out, it broke a lot of stuff. Okay. And basically this was always going to try. We were always going to try and put this into like Regina, which meant it was always going to have to get a C++ rewrite probably at some point. So the quickest solution to both of these problems was to burn it all to the ground and start again in C++.
Right. So Regina's like the faster, like the better package ultimately. Is there anything to do with like speed? Because I know C++.
Oh yeah. So the Python version of this software was of my implementation of this. Like if I go back to sort of the screenshot of it, so it gives like it generates all these, you know, crossing graphs and curl graphs, and you know, you would give it this encoding of the diagram, and like the Python version, it would there go chunk 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 printing stuff out, whereas the C++ version, it does it in, it's almost instantaneous. So the speed is just, it's phenomenally faster. Yeah.
No. Well, thanks for clarifying that, because I was curious.
Yeah. So speed, but also
not an interesting mathematical question, but
that's okay.
a good question nonetheless.
My question was, how does this kind of fit in with homology spheres and whatnot?
To what extent? Because for example, the boundary of this cork is a homology sphere. I mean, what would you like to know?
I guess, like, I'm wondering, are there any kind of examples which come up from looking at homology spheres or something like that, or is it?
Oh yeah, well, so one thing you might wonder, right, is that okay, given a 3 manifold, does it bound a pair of exotic 4 manifolds? And there's been some, I can't really say anything too intelligent on that front, but I know there is work on sort of like, if you've got a homology 3 sphere, which ticks some boxes and, you know, you satisfy a bunch of hypotheses, then there's sort of like there is I think some way of not generating, like I don't think there's like an algorithm or anything for it, but I can tell you that there exists a pair of exotic 4 manifolds with that homology 3 sphere as boundary, I think, but maybe don't quote me on that. But there's definitely stuff going on here, because and actually it's like when I said that we're trying to you know, pin down what the actual combinatorial version of this involution on the boundary of the cork is, because it's on the boundary, right? The boundary is a homology 3 sphere, so you're here looking at basically isometries and maps on 3 manifolds now, and in particular, right? And in particular, for the case of the cork, it's hyperbolic, so that really sort of you know, restricts and narrows down what can happen. So we're kind of we wind up back in 3 manifold land to a certain extent. But yeah, I don't know what else I would really say on that front. But there's definitely stuff going on there. Like it pops up here and there. Yeah.
I might ask a question. So in your table of your minimal triangulation stuff.
Yeah. Well, minimal asterisks.
Yeah, minimal in this sense.
Yeah.
So the original effectors are not the same for these pairs. Is it obvious?
Yeah,
like, did you expect that your new vectors would be the same?
Well, yeah, because like I said, because if you can get down to one vertex, one vertex, one edge, it's completely determined by the second Betti number. So if you know, because they're homeomorphic, so they should have the same topology, so they've got the same Betti number, you'd hope that you'd get down to the same effector if you can do this 1B, 1E sort of thing.
Yeah, cool. Okay.
Which I should maybe mention, like, I mean, there's no reason as to, like, we didn't really expect, or at least my supervisor Ben, he didn't expect that would be able to get down to one vertex and one edge on these things. For some of these, like there's pretty much no, we don't really know. There's no theorem as to why or when you can get down to one edge, for example. I mean, okay, so I think you should always be able to get down to one vertex, which is another thing that we're working on. But whether you can always get down to one edge is wide open. I mean, and we know other than you need to be simply connected, because then you get stuff from first homology that interferes with things. But if you simply connected, aside from that, there's no reason as to why we would have been able to expect for this to work. So it was just sort of it was when it worked, it was like awesome. Yeah.
Okay, are there any other questions for Rhuaidi?
Yeah, actually, I was wondering about when you're showing, well, yeah, I haven't quite kept up, but like, do you show a homeomorphism or diffeomorphism between the A1 and A2? Towards the
Sure. I mean, so the showing homeomorphisms of all these things, especially for A1 and A2, like for example, this isn't too difficult in that, like I said, these guys, the topology is captured by their intersection matrices. So it's like a bilinear form on the second homology. If you've just got knots, then this is like the intersection matrix here is literally just the framing on the knot. So you can see like straight away, you'll get you've got isomorphic.
So a bit,
on this guy.
later on,
and so by a result of Friedman, that says that they're homeomorphic.
Right, and then later on with the Akbulut core, you use a boundary diffeomorphism.
No. So there's an involution on the boundary, and and so because it's on the boundary, you're in three manifold world, and in three manifolds, homeomorphism is diffeomorphism. So you've got a diffeomorphism if you like on the boundary of the cork. It extends to a homeomorphism of the whole thing, but not a diffeomorphism of the four manifold.
Ah, right. Okay. So this is how you can show non-diffeomorphic.
Yeah, but it is subtle in the sense that just because you have one of these things sitting here doesn't necessarily mean if you cut and paste it'll work. It's sort of like you have to know that, like, it's easy if you give me a pair and you say that if you give me a pair of exotic four manifolds, then there's actually a theorem which says that every pair of simply connected exotic four manifolds differs by a cork twist. So if you give me the pair, you can try and find the cork that changes the smooth structure. But that's like, I say you do it, but it's not a trivial thing to do.
Oh, so will these things always have diffeomorphic boundaries?
For this class of four manifolds, yes, they should have diffeomorphic boundaries.
Okay, so like you basically have like a little bit more access to like blow up and blow downs and stuff like that as well.
Yeah.
Okay. Cool. Thank you.
Great. Well, I might stop the recording there. If we thank Rhuaidi once again.